So good afternoon, everyone. Welcome to our presentation. Today we want to share our research towards the realistic single-image super-resolution task with you. The title is Human-Guided Ground Truth Generation for Realistic Image Super-Resolution. And I am the presenter, Du Chen. I come from the Hong Kong Polytechnic University. In this paper, we elaborately designed a human-guided ground truth generation method for realistic image super-resolution. We first trained 4 image enhancement models to improve the perceptual quality of original high-resolution images, and then extracted structural and textural patches from the enhanced images. Finally, human subjects were invited to annotate the perceptual quality of extracted patches as positive and negative GTs, resulting in the human-guided ground truth dataset. We call it HGGT dataset. The sharper textures and richer details in the positive GTs could largely improve the performance of trained real ISR models, while the negative GTs could provide further guidance for the model to avoid generating visual artifacts. Extensive experiments validated the effectiveness of the proposed HGGT dataset and the training strategies. Firstly, as for our motivation, we observed that, in many training datasets towards the SISR task, the ground truth images sometimes do not have very good perceptual quality. There may exist blurry details or noisy areas. Secondly, manipulating the GT generation progress has not been well explored before, and nearly all of the SISR researches do not consider human perception in GT generation. Thus, with the poor perceptual quality of the training GT images, SR models tend to produce oversmooth results or unpleasant artifacts. Based on those observations, we firstly trained multiple image enhancement models to improve the perceptual quality of HR images. One LR image having multiple HR counterparts. Then, human subjects are then involved to annotate the high-quality regions among the enhanced HR images as positive GTs, and label the regions with unpleasant artifacts as negative samples. So we construct a human-guided image dataset with both positive and negative GTs. At last, we train realistic SR models on the proposed HGGT dataset. Experiments show that the real ISR models trained on our dataset can produce perceptually more realistic results with less artifacts. The proposed human-guided GT generation method has 3 steps. First, we elaborately train multiple image enhancement models to improve the perceptual quality of HR images. Second, those patches which have enough textural and structural details and have certain differences between the enhanced version and the original version are extracted. Third, human subjects are introduced to discriminate the visual quality between the enhanced patches and the original patch, and label them as positive if the enhanced images have better quality, similar if they share similar quality, or negative if they have worse quality. After the annotation progress, we could see that positive images occupy the vast majority of the quantity, while there are few negative images. So it proves that the perceptual quality of already existing GT images could be still enhanced, since they are not very perfect. Finally, we call our proposed dataset as HGGT dataset. After constructing the whole HGGT dataset, we just train super-resolution models via them. Since we have positive and negative pairs, we are supposed to validate their effectiveness respectively. Firstly, we only train the models with positive pairs only. By removing those groups that do not have any positive GT from the 20,193 training groups, we have 18,926 groups, 63,583 positive LR-GT pairs. Each time we randomly choose one positive GT to train the model. Then, taking the negative samples into consideration, we train models both on positive and negative pairs. By removing those groups that only contain similar GTs, we obtain 19,272 groups that have at least one positive or negative GT. Totally 63,583 positive LR-GT pairs and 2,514 negative LR-GT pairs. We observe that most of the negative GTs have over-sharpened details, strong noise or false details. We build a negative map to locate the local residual variation of a negative GT, as well as a residual variation positive map for the positive GT. Finally, we obtain the indication map, which indicates the truly negative pixel. So we train the models with positive and negative pairs, and define the overall loss functions. Now let's see the qualitative results of our experiments. Firstly, we will show you the effectiveness of the positive GTs. The first row shows the results of the models trained with the original GT images, while the second row shows the same models trained with the positive GTs which come from our proposed HGGT dataset. When compared with the models trained with the original GT images, the models trained our proposed HGGT dataset could generate much clearer details and more sharpened textures. Then, as for the effectiveness of the negative pairs, as you could see, the second, third and fourth column shows the models trained on original GT images, positive GT images, both positive and negative GT images respectively. The models trained on positive GT images could generate much clearer details, whereas there remain some false details and visual artifacts. While the models trained on both positive and negative GT images will lead to a more balanced visual performance. Some over-enhanced local pixels can be suppressed, while the textures remain sharp and regular. As for the quantitative results, the models trained on our positive GT images or both positive and negative GT images have much better LPIPS and DISTS values, which indicates that our proposed HGGT dataset could surely improve the perceptual quality of the reconstruction results to a large extent. The main goal of the proposed HGGT dataset is to improve the perceptual quality of the reconstruction outputs by introducing human perceptions into the training pair generation. We perform a user study to validate the effectiveness of our strategy by inviting some volunteers to evaluate the results. As shown in this figure, the majority of participants, more than 80% for all tests, prefer the models trained on our HGGT dataset. This validates the effectiveness of the proposed approach in the dataset, which can be plug and play to most of the existing real ISR methods and improve their performance by a large margin. That's all of the contents towards our proposed HGGT dataset. Many thanks for your listening.